we, magnitude and length are sometimes used interchangeably. The notation for the length of a vector is put vertical lines on either side of it. That means the magnitude of the vector. And direction. So it's an arrow. The best way to represent a vector is in terms of its components. The best way to tell somebody else what vector we're talking about. So you lay out some coordinates, x, y, z, and here is my vector. I drop the perpendicular down into the xy plane. And the coordinates of that vector, the components of that vector, are a sub x in the x direction, a sub y in the y direction, and a sub z in the z direction. It's handy in this business to introduce unit vectors. Along each of the three coordinate directions. By unit vector, I mean length 1, magnitude 1, and pointing along each of the three coordinate directions. So here would be the unit vector along the x direction, I hat, the unit vector along the y direction, j hat, and the unit vector up the z direction, k hat, I hat, j hat, and k hat. And in terms of those three coordinate unit vectors, we can express the vector A as component in the x direction, the x component, I hat, plus the y component, j hat, plus the z component, k hat. There's the cleanest notation for a vector. What that says is go in the x direction and amount a sub x, then in the y direction and amount a sub y, and then up in the z direction amount a sub z, and you will arrive at the head of the vector. So just nice notation. I told you last time how to do all of vector arithmetic, add vectors, subtract vectors, so on, both in abstract form and in component form. I want to remind you just of one of these because this is one that's likely to be unfamiliar to a lot of you. That's the dot product. The dot product of two vectors, A and B. Here's B and here's A. And let's say that the angle between those two is theta. When I put them tail to tail. Small angle, of course. Some people say, oh, well, two angles between A and B. That's right, because there's other angle here. I'm not talking about that one. The dot product between A and B is written A dot B equals, it's the length of A times the length of B, the magnitude of A times the magnitude of B times the cosine of the angle between the two. And in component form, if I had expressed A and B in terms of their three components, this would be A sub x, B sub x, plus A sub y, B sub y, plus A sub z, B sub z. The product of the x components plus the product of the y components plus the product of the z components. The dot product is itself a scalar. It takes two vectors and spits out a scalar, a number with no direction attached to it anymore. And for that reason, it's sometimes called a scalar product. In fact, I noticed that the book preferentially calls it the scalar product. I call it the dot product. The fact that the dot product, which is defined as length of A, length of B, cosine of the angle theta, is also equal to the sum of the products of like components of the two vectors. That's a kind of surprising fact. I didn't derive it in class. You can read the derivation in the book. It's not one of those derivations that does anything for you. You just read it through, and there it is. And you convince it is true. But the important point is that you can write a dot product in either of those two ways, This way, if you happen to know the components. This way, if you know the lengths of the vectors, the magnitudes of the vectors, and the angle between them. Playing those two off against each other, however, can be enormously powerful. I want to run you a simple example of this. Just an illustration, if you like, of the dot product and its power. Problem. Find the angle between the face diagonals of a cube. I'll tell you in a second what those are. Well, it means take a cube and draw a diagonal across any face. I don't mean a body diagonal going right through the center of the cube, but just across any face. Take two of those from a given corner, and I want to know what the angle between them is. Let me see if I can draw this. Here's the cube. Not too bad. Practice. So, what do I mean by the angle between face diagonals? Here's one face diagonal across that back face. And another face diagonal would be, well, this one across here. I'm going to actually use this one up here that goes to that back corner there. You see that this one is a diagonal across the left face. This one's a diagonal across the back face. Got the picture? And my question is, what's that angle there? If you happen to know the angle, by the way, keep your mouth shut for just a minute because the others don't. So that's the problem. Here's a clever way to do this. This is something that would come up if you were a crystallographer, for example, all the time. How do you figure out that angle there? You can spend an afternoon trying to figure this out by geometry. It's not in principle. Well, this particular one, I'll show you another way to do it in a second that makes it easy. But all kinds of problems of this generic type can be a nightmare to try to figure out if you don't have vector notation to work with. Let me show you how to do it by vector notation. I'll introduce two vectors. The vector along the diagonal across that side, and the vector along this. I'm going to call this vector A and this vector B. What are those vectors in component form? Well, gee, how big is the cube? How big should we make it?
1.
1. Why not? Obviously, this angle doesn't depend on how big the cube is. So let's give this dimensions 1, 1, and 1. This the x direction, the y direction, and the z direction like that. Now, let's see if you can tell me what is the vector A in this notation here. What's the x component of A?
1.
1. Very good. I have to go out the x direction 1 unit. What's the y direction, y component of A?
0.
0. Very good. I don't go in the y direction at all. And the z component? 1 again. Everybody see where we're getting those? Because that's the essence of this problem. I go 1 unit in the x direction, nothing at all in the y direction, and then 1 unit in the z direction. So 1 k hat. Same job on B. For B, I would go, now this is a vector to that back side. What's the x component?
0.
0 in this case. I'm not going to go in the x direction at all. That back face is entirely in the yz plane. So it's 0 I hat plus y component, 1, and z component, likewise 1. I'm going to go from here, nothing in the x direction, 1 unit in the y direction, 1 unit in the z direction. That'll give me the vector B. Hey, what's the length of A? I forgot to write down the general formula here for the magnitude of a vector in terms of its components. I think I mentioned this last time. It's the sum of the squares of the three components.
Root 2. Root 2.
Root 2, isn't that right? Because it would be the square root of 1 plus 0 plus 1, so it's the square root of 2. How about B? Likewise, the square root of 2. Of course, they're both the same length there. 0, 1, 1, square root of 2. Now, how about A dot B? Well, I can construct A dot B in two different ways. I could use this expression here, which says length of A, length of B, cosine of the angle between them. Oh, I don't know. Well, but that's exactly what we're trying to find, is the angle between them. So that just leaves that in there in the form of cosine theta. Fair enough? So that's the dot product written out in this language. It has a theta in there, but that's exactly what I'm trying to get my hands on. On the right-hand side, however, it should be the sum of the products of like components. Well, with A sub x, B sub x, B is 1 times 0. A sub y times B sub y, 0 times 1. A sub z, B sub z. And the answer is 0 plus 0 is 1. Ah, how nice. Now I've got it, right? Cosine of theta, if I read this and this, it says that cosine of theta is equal to root 2 times root 2 is 2. So pull that over to the other side, is 1/2. You happen to know the angle whose cosine is 1/2? 60 degrees. This is a triangle that every student of physics should memorize, I think. 1, 2, square root of 3, the 30, 60, 90 right triangle. 60 degrees, 30 degrees. So the cosine of 60 degrees would be the nearby side, 1 over the hypotenuse, 1 over 2. So theta is 60 degrees. Everybody satisfied with that? The answer is neither here nor there. It's the technique I'm interested in. If you want to know the angle between two lines, represent one by one vector, the other by another vector, figure out what their components are, and then calculate the dot products by two different methods, and that's going to spit out for you what the angle between them is. Very clever. The book does a kind of an example like this, which I was delighted by, because most books don't even mention this as one of the powerful applications of the dot product, something that I learned just from having to solve problems like this in real life a lot. Anyhow, where are we? Oh, does this angle 60 degrees sound reasonable? Well, I'll tell you what, if I'd been on the ball, I could have put this third face diagonal across the top, right? And now look at what I've got. 3 face diagonals forming a triangle. And obviously all 3 got the same length. So that's an equilateral triangle, and the angle in an equilateral triangle is indeed 60 degrees. So if you had had the wit to complete the triangle there, you could have spotted the 60 degrees immediately. But I tell you what, if you think that this is trivial and you could always do it like that, try calculating the angle between the body diagonals of a cube. That's the one that would go from here across to there, and from here across to there. They cross in the very center of the cube, and that's not an angle, so far as I know, that you can get simply by any kind of construction like that. But the vector method gives it to you very simply. Enough on that? That was just an example of the power of the dot product, and in particular, the power of using the fact that you can represent the dot product in 2 different ways. Now, what is this all for? In our case, we're interested in kinematics, setting up the theory of motion in 3 dimensions. You know how to do kinematics in 1 dimension. 3 dimensions is just the same, only everything becomes a vector instead of a scalar. So, whole lot to be said here. Position. I want to know where some object is. So x, y, z, here it is, and it's buzzing around. It's a v or something like that. Right at the moment, it's out at a vector position that we call r. R is the, I don't know why the letter R, but the position vector is r, which is going to be a function of t as that v flies around. What are the components of r? If this thing is right now at the point x of t, y of t, z of t, then the components of r are nothing but x, y, and z. So r is x of t in the I hat direction, plus y of t in the j hat direction, plus z of t in the k hat direction, where x, y, and z are simply the coordinates of the point in question, or the object in question, at this particular moment. And of course, as time goes on, the thing flies around, x, y, and z are all going to change, therefore the position vector r is going to change. Nothing deep there. How about velocity? Again, is now going to be a vector. V of t, the velocity vector, is defined in the same way as before, only it's a vector with three components. Actually, in a way, all I'm doing is doing kinematics 3 times over and packaging it in the form of a vector. It's dr by dt, by which I mean dx by dt in the I hat direction, dy by dt in the j hat direction, dz by dt in the k hat direction. So just differentiate the 3 components of the position vector and assemble them. That's the velocity vector. By the way, those 3 components, if I think of them as components of v, that would be v sub x, itself a function of t in general, plus v sub y, function of t j hat, plus v sub z, k hat. In other words, v sub x of t is dx by dt, and v sub y of t is dy by dt, and v sub z is t is dz by dt. Okay, 2 technical matters now. Speed. Remember what speed was in one direction, in one dimension? It was just the magnitude of the velocity, never mind which way it's going, never mind the plus or minus sign. We generalize that now so that speed in 3 dimensions means number of miles per hour regardless of direction. It's the magnitude of the velocity vector. Vector, the magnitude of that, in other words, the square root of the sum of the squares, would be the speed. How about average velocity? This is the instantaneous velocity. What if somebody asks you for the average velocity? Over some interval. Delta t, well, that's generalized directly for the one-dimensional case too. The average would be the distance gone, no, not the distance gone, the displacement vector, delta r, r final minus r initial, the difference of the 2 vectors, divided by delta t. So it's the vector displacement from the beginning point to the end point divided by the time. If something goes around like this and comes back to its beginning point again, what was its average velocity over that interval?
0.
0, right? Because its net displacement was 0. Now, a term that I personally would never use, but it does come up on one of the owls, so let me mention it. Average speed you could define the average speed as the magnitude of the average velocity. That would seem to me possible. But then you would get into the weird situation that I would have to say for a case like this where the thing went around a loop, came back to the beginning, that its average speed was 0. Is that what you really, because the average velocity is certainly 0, if it came back to the beginning, do we really think, would we like to be saying the average speed was equal to 0? I don't think so. What would you mean by average speed in that case? I guess it's the total distance that you traveled, never mind what direction it was in, divided by the total time. Is that what you were going to suggest? So let's, as I say, this is a very seldom used term in this business, but I think it makes sense to define average speed as total distance traveled regardless of direction. So if it comes back to the same point, the distance it traveled is not 0, it's the whole length of the path. Over delta t. I mentioned that mainly because you're going to get that last one on one of the owls, and so you understand what the word means. There it is. Okay, enough on velocity vector. The third item, of course, is acceleration. So we're down to position vector, velocity vector, acceleration vector. Just do the same thing again, of course. A of t as a vector is dv, as a vector with respect to t, so that would be dv sub x by dt in the x direction, dv sub y by dt in the y direction, dv sub z by dt in the z direction. And if you like, this is a sub x, this is a sub y, y component, and this is a sub z.
David, did you want to stress that the average speed is not the absolute value of the average velocity?
Right. Good point. I think I said it, but I said it before I told people what average speed was, so probably they didn't, people didn't pick that up. Is that clear? The average speed is not the absolute value of average velocity. That indeed would give you 0 if you ran around a closed loop. Then the average velocity is 0, but the average speed is not.
But speed is absolute value of velocity.
Right. Right, so the terminology is a little slippery here. I think that it would have been perfectly okay if somebody had said, I define average speed as the absolute value of average velocity. That would have been a possible game to play, but it would have led to a very peculiar notion of average speed. I think that's why my example of going around a closed loop was trying to motivate why this is maybe a more sensible definition of average speed than absolute value of average velocity. The main point is this is not a big deal at all because, as I say, this is pure terminology and terminology that I personally would not ever use anyway, but just to warn you, what is average speed in 3 dimensions? Little red flag should go up. This is tricky. I better think about what it is. Distance, and what it means, the way it's defined is the distance, total distance traveled along the path divided by the time it took. Now, there's one profoundly important thing about the vector kinematics that is a whole new idea, and this is going to come on Monday as a real bombshell. Well, it won't for you because you probably already studied circular motion, but it is a profoundly important fact. If the direction of velocity changes, that's acceleration every bit as much as if the speed, the magnitude of the velocity changes. So I'll put that down as a parenthetical remark here, and on Monday you'll see the importance of this. I think sometimes that this is the observation that must have been made by Newton first, that actually cracked open all of classical mechanics and therefore led to all of physics. That's not too dramatic a way to put it. If the direction of velocity changes, that constitutes an acceleration every bit as much as if the magnitude changed. So if you're going around a circle at a constant speed, you are accelerating. Not speeding up, not slowing down, foot off the accelerator, I don't care. If the direction of your velocity is changing, then you're accelerating. If the direction of velocity changes, magnitude of the velocity changes, then of course we will all agree that that's acceleration. The car is speeding up or slowing down. But if the direction of the velocity changes, you go around a corner, that also is acceleration, and this is a profoundly important realization. Something that people before Newton, I guess the Greeks certainly, wouldn't have thought that was true. Something going at constant speed, not accelerating, but it involves thinking carefully about what you mean by velocity and acceleration. If the direction of velocity changes, that constitutes acceleration just as much as if the magnitude of the changes. So there's just a warning, an anticipation of things to come. Now I want to talk a little bit about relative velocity, and I guess this is really an application, a standard application, but one for some reason that I always find very elusive, difficult for me to think about this kind of problem. Maybe it isn't for you, but this is the subject of relative velocity. I'm going to build up the theory by doing some examples that'll start out really stupidly easy, but are building up to the basic conclusion. Relative. That's the velocity of one thing relative to another. How do you play with such ideas? Here's the example. Here's an example. You're provided with a motorboat that has a motor that only goes at 4 kilometers per hour on still water. Got it? So we take it out on a pond where there's no current flowing or anything like that. Turn it up full blast, goes 4 kilometers per hour. But now I plan to load that motorboat onto a river. The river is flowing at 3 kilometers per hour. And now I'm going to figure out what your net velocity is for various different directions that you might propose to aim. So here's the river. It's flowing this direction, and it goes 3 kilometers per hour. here's your boat, and it goes in still water 4 kilometers per hour. I gave away what the first question is. Suppose that you aim it straight downstream. Question, what's your net speed? Your speed relative to the bank, in other words. Answer? 7. Is that pretty obvious? You're going at 4 kilometers per hour, but you're drifting downstream at 3 kilometers per hour. Your net speed downstream is 7 kilometers per hour. That would be 4 plus 3 equals 7. Make sense? If you're bothered by it, you could imagine, let's let this operation go for 1 hour. How far did I go because of the motor? 4 miles. How far did I drift because of the stream? 3 miles. Total distance I went? 7 miles. Velocity, therefore, 7 miles per hour. That's our speed. Actually, let me anticipate by putting in some coordinates here. This would be the y coordinate and the x coordinate. I don't need any z for this problem, of course. Your velocity, I'm going to say v sub n, that means net velocity relative to the ground, is equal, in this case, to 7 kilometers per hour, and it's in the I-hat direction. So far, so good. That's supposed to be obvious. Second, upstream. If I turn this thing around and go upstream, bucking the current, I ask you the same question. What's your net speed now relative to the ground? 1. For minus 1 equals, whoops, 4 minus 3 equals 1 kilometer per hour. Pretty obvious. Your net velocity in this case as a vector is, it's going in the negative x direction, minus 1 kilometer per hour in the I-hat direction. Actually, in the minus I-hat direction, minus. So far, so good? Yeah.
Wouldn't it be the negative 4 plus 3? Just want to be consistent.
Okay, I was talking about speed here, so I ducked your question. If I had been adding the velocities, that's right. I would have said minus 4 in the I-hat direction, plus 3 in the I-hat direction. That would be a more systematic way of doing it, and I would come out with minus 1 kilometer per hour, and then I would say, so what's the speed, the magnitude of that? That would wipe out the minus sign.
Okay.
So minus 4 plus 3 over 3 minus 4. Because
Okay, you people are really formal. What is the net velocity?
Well, I
Just
know.
let it go.
It is minus 4 I-hat plus 3 I-hat for the stream is minus 1 I-hat. That's the velocity, and therefore the speed equals 1.
Yay.
Much better way to do the problem, by the way. I don't mean to put that down. I think you're quite right. That's a better way to do it because it anticipates exactly what I'm leading up to. Is of course the general theory. How do you handle this when you know the boat's going at 45 degrees or 47 degrees, some nasty thing, and the water is going some other way or something? How do I handle the general case? That's what I'm leading up to. So better to be formal about the notation even at the beginning. everybody agreed that the speed, though, is 1 kilometer per hour. What, by the way, if the river was going at 4 kilometers per hour? Then you're dead in the water, right?
Kind of move. Yeah, this one.
Okay. Now suppose that you aim straight across. You aim the boat, watch what the language is here. You aim the boat straight across. What's going to happen then?
Go off at an angle.
You will go off at an angle, and I want to find out exactly what that angle is. So C. Okay, so here's the river. I'm going to aim straight across. So if I think about it, suppose that I did this for 1 hour. This is a nice wide river. If I did it for 1 hour, I would have gone 4 kilometers in that direction. But the river, meanwhile, has dragged me 3 kilometers downstream. So I would actually wind up at this point here, and we might be interested in knowing what my net velocity vector is in this case. What would you say? At 4 kilometers per hour across, 3 kilometers per hour downstream, in that same language, what is your net velocity? Net speed is 5. You're ahead of the game. Net velocity, because I'm trying, having been educated by these two, I'm trying to be very formal about velocity first. Velocity is 3 in the I hat direction plus 4 in the j hat direction. Speed, that's the magnitude of the velocity vector, would be the square root of the sum of the squares. 9 plus 16 is 20, square root of 25 or 5. Of course, there's a 3, 4, 5 right triangle. So if you said, what's my net speed? My net speed relative to the ground is 5 kilometers per hour. Make sense? What angle am I going at? What angle downstream? It's not 30. This is not a 1, 2 square root of 3 right triangle. It's a 3, 4, 5 right triangle. I don't know if you happen to know what that angle is. I can never remember it, but 3, 4, 5 right triangle. What I want is the angle whose tangent is 3/4. Isn't that right? Or whose sine is 3/5 if you prefer. So it's arc tangent of 3/4. You write it like that, or I prefer actually the notation 10 to the minus 1 of 3/4, whichever way you want to write it. It's that angle whose tangent is 3/4. The inverse tangent of 3/4, I looked it up, and the answer is 37 degrees. Approximately 30, 37 point something. So, you aim the boat straight across. You're going to be drifting somewhat downstream. At what angle are you actually going? 37 degrees. The boat is at all moments pointing straight across, but because of the drift in the stream, it actually moves along that diagonal line with a speed of 5 kilometers per hour and at an angle of 37 degrees downstream from straight across. Suppose that this stream was exactly 4 kilometers wide. How long would it take you to get across?
More than
1 hour. Exactly 1 hour. Because in that direction, you've been going 4 kilometers per hour. How far downstream would you hit the bank? 3 kilometers downstream. How far did you actually travel? 5 kilometers along the diagonal line. Yes, actually they are. But you have to read the fine print very carefully. I said, what if you aim straight across? Suppose that you ask a different question. You say, I don't want to land 3 kilometers downstream because that's where the crocodiles are. I want to land directly across. What must you do in that case? You better aim a bit upstream, huh? So here's another question, a different question. In order to land directly across, you'd have to aim somewhat upstream. If you aim straight across, you're going to land downstream. But if you aim somewhat upstream, question, how far upstream, at what angle upstream will you have to aim?
37.
Nice try. Hold on to that. In order to land directly across, you'll need to aim upstream. Question, at what angle? Okay, let's draw the picture here. I now am going to aim upstream like this at some angle, such that the velocity of the stream pulling me back, that's at 3 kilometers per hour, will lead to a net velocity that's straight across. Right? Watch out, especially all of you who said it's 37 degrees. This is your velocity relative to the water. That was 4 kilometers per hour. This is the velocity of the stream, 3 kilometers per hour. What is this angle theta that you have to aim upstream at? Do you see the problem? It is not the arctangent of 3 over 4. In point of fact, it's the arc sine of 3 over 4. Right? Because the sine of this angle is the opposite of the hypotenuse. So the answer is theta in this case is equal to arc sine